Guys, we're going to do some calculated earthquake force on structures with examples from NZS 1170.5. So have all of you downloaded the codes that I messaged you guys earlier? Okay, let's make a start. Height of structure and period. A structure that is taller will typically vibrate more slowly than one that is shorter. Okay, that means its period will be longer. Think of two plastic rulers of the same material and cross-sectional dimensions. Which of the two will have a longer period of vibration when flicked by the same hand motion? I'm sure most of you will be able to see that it will be this one on the left here. So let's have a look at a couple of videos. Okay, it's a short ruler. I think that's a pretty good illustration. Okay, the more mass, basically, the longer the ruler is, the more mass there is, right? You can see that the period of vibration gets lower. Okay, whoops. Let's see. Okay, so let's have a look at this one.
I think we should explore a few solutions.
Grab these suggestions, catch when your tone might undermine.
Here's an activity you can try at home. All you need is a 30-centimeter ruler and a countertop. Place the ruler so the first 7 centimeters are flat on the counter and the rest of it is extending off the edge of the counter. Lean on the 7-centimeter segment that is on the counter so it is held firmly in place. Then, with the thumb of your other hand, pluck the end of the ruler that is extending off the counter so it vibrates up and down. Note the sound that it makes. Now repeat the process, but move the ruler further back on the counter so 15 centimeters are flat on the counter and the other half of the ruler extends off the counter. Listen to the sound the ruler makes when you pluck it. Once more, slide the ruler farther back on the counter so 23 centimeters are flat on the counter and only 7 centimeters extend off the counter. Again, notice the sound the ruler makes when you pluck it with your thumb. What did you hear? Did you notice that the ruler sounded differently depending on the length of the ruler that was able to vibrate? When a longer section of the ruler could vibrate, it sounded deeper than when we plucked shorter sections. You can perform this experiment at home.
Okay, so what does it mean? That the deeper a sound is in terms of sound waves, right, the larger the period. Okay, so the more mass, the higher the building, you can see that it will vibrate slower. That means you've got a higher period, lower frequency. Okay, response spectrum. And we've talked a little bit about this before we went for a break. With building structures, taller structures, as the case of the ruler, typically increase in period with height. For a given earthquake acceleration record, the maximum response acceleration can be plotted against the period t. So imagine if we had these buildings, typically as they get higher, the period increases, right? So we can plot the period here. Okay, imagine if you had the same ground acceleration, and you can plot what we call the maximum response acceleration. Okay, maximum acceleration of the structure in response to the ground motion. Okay, so remember the reason why we do that is we want to know something about the mass. We have the we know something about the mass. If we have the acceleration, then we can start working out some forces through force equals ma. Now let's have a look at the situation in New Zealand in terms of spectra. What they do is they the codes provide you with an average spectrum based on the historical earthquake records of a particular region. In New Zealand, NZS, the New Zealand code, NZS 1170.5, section 3.13, we start off with a spectra shape factor as follows. So they give us the starting spectrum, which we have to adjust. Okay, now you see the spectrum, okay, you've got unit of acceleration along here of G, and they call it the spectral shape factor. So it's a very generalized spectrum first that you're going to adjust for various other criteria. Notice that we've got different soil types. We have different spectrums. If you have soil types A and B, you got soil types C, D, and E. Now, A and B refer to rock. A is strong rock, B is weak rock. Okay. C is what we call shallow soil types, probably quite typical. D is deep or soft soil types, and E is very soft soil. So the softer your soil for the same type, the same period building and the same earthquake, you're going to get a higher acceleration, response acceleration of that structure. And some examples of that are Christchurch, where you have soil type D. Okay, so actually the accelerations at Christchurch were underestimated. They've been raised now. I think they were about 0.22 before. For I'll come on to it later, but they've been raised by about 1/3. Okay, but in places where you've got alluvial or lacustrine, I think they call it lacustrine deposits, like in a lake, like Mexico City, you might have something like soil type E, which is very soft soil. Okay, so buildings that are founded in areas of very soft soil, they can often be subject to a lot higher, they have to be designed for much higher seismic resilience. Okay, so again, note the different foundation soil types have different spectra. The same structure built on soil type E will react much more violently to the same earthquake as a structure founded on soil type A or B. Okay, so this is, this is a code there that perhaps you guys can see. If you haven't downloaded already, download this code. Okay, if you've already downloaded it, you don't have to do it again. Okay, so this is your starting off spectrum, right? It's not but you have to adjust it based on various criteria. And what we're going to do is look at these criteria now in the next slide. Okay, so what we're going to change it to is now, before you called the site hazard spectra, CHT, which is the norm, sort of like the general spectra for New Zealand. Okay, now we're going to modify it to get the elastic site hazard spectrum CT. So instead of CHT, we've got CT. A little bit confusing, but it's not really. Okay, so the elastic site hazard spectrum is the one we use to find our response acceleration for structural design. It modifies the site hazard spectra, and it takes into account the following: the site location in New Zealand. Now that makes sense, right? Wellington's going to, we're going to modify these values based on the location, which makes perfect sense, because most of you will know that Wellington or even Napier will have a higher, much more seismic than say Auckland or Northland. Okay, so the site location in New Zealand, and this is given the name hazard factor, and it's got a symbol Z. We have the earthquake return period, RU or RS, where RU is for ultimate limit state and S is for serviceability limit state. And that makes sense as well. Like are you going to design for a 500-year earthquake, a 1,000-year earthquake, or 2,500-year earthquake? As you know from last week when we talked about wind loads, the bigger the return period, or the bigger the magnitude of wind, or the bigger the magnitude of the earthquake, right? So what do we mean by a 1,000-year earthquake? It means it will, on average, it will happen once every 1,000 years. So a 500-year earthquake, on average, it will happen once every 500 years. Okay, so this is important as well. Well, obviously very important, the return period. And the other one is how close the site is to a major fault, and that's called the near fault factor. Okay. Now, for our purposes, we're going to just assume that the near fault factor is 1. So we only have to deal with this value, which comes from the previous site hazard spectra, this value here. We only have to, and the location and the return period, just 3 things. And then we can get our response acceleration. Okay, we're doing it in a, I suppose, simplified way. And in the code, it's given to us in terms of G. Okay, so here's an example. For a structure of fundamental period T equals 2 seconds and founded on soil type D in Hastings, determine the response acceleration. The importance level of the building is 2 and the design working life is 50 years. And we need to consider both the ultimate limit state and the serviceability limit state. Now, here's the 1170.0 to get the importance factors. I'll see if I can bring that up so you guys can download it if you haven't done so already. Okay, so I suggest the first thing you got, this is your equation. Okay, you can do it in pretty much, let's see what order, I'll suggest what order you should do it. Let's just give me a second. Okay, first thing you should do perhaps is, you don't have to do it in exactly the same order, find CHT. Okay, so I suggest you find CHT first, okay, based on the information that I've given you here. Now I've given you the table numbers and the figure numbers, okay? So you guys give it a go and take into account it's soil type D in Hastings. Okay, so have a go at finding CHT. Just do that first. Hey guys, we can find it in pretty much any order. So what we do is say if we wanted to find Z, right? That's the site hazard factor. What we do is we can go to this map here. Okay, well, we can use a table as well. So if you look at Hastings, right, but this is not Hastings, it's 0.39, okay? And you can also find it from the contours here. So you can see Hastings, close to Napier, 0.3 there, 0.4, it's about 0.39. Okay, so your Z will be 0.39. Now let's look at our return period factors. We look at this code here, which you guys have some familiarity with. We're given a importance level of 2, we're just given that. Okay, so, and we're given a design working life of 50 years. So we're 50 years and we've got 2. Now, last week we looked at wind, this week we're looking at earthquake. So we've got a 500-year earthquake, which is pretty much the same as wind. And serviceability, we've got 25 years, which is again the same as for wind. So that's quite straightforward. Now, let's have a look at, so you've got, we find CHT from figure 3.1. Okay, oh, sorry, don't do Z. We've got Z, okay. We've got R now, okay. Well, we know the return period. Okay, we've got to multiply it by what we call the return period factor. So sorry, I think I got you to, all we need to do is find Z. Okay, I shouldn't have asked you to find, you've got the return period, but I'm going to teach you to find the return period factor, which is a different thing. So just bear in mind, sorry, 500 years for ultimate limit state, 25 years for serviceability limit state, but we'll look at R in the next soon. Now, what I want you guys to do is find CHT, okay? Now, CHT is in your code, okay? And let's have a look at figure 3.1. Here you go, 3.1. Or you can even look at the table, okay? If the period is slow, it corresponds, if we got it there. So you guys look at the table or this to find CHT, okay? So do that now. So what we've got is, we've got Z, we've got the return period for ultimate, return period for serviceability, but that's different from the return period factor, so it's a little bit confusing. So just that's 25, that's 500, and we've got 0.39 for Z. Now I want you to find CHT, which is the site hazard spectra. Okay, so go to figure 3.1 or table 3.1. Okay, so do that, find CHT. Okay, for your CH site spectral shape factor, right, you should, if you have 2 seconds, if I go to the table and what type of soil I've got, soil type D. Okay, so 2 seconds soil type D, I've got 1.07. I can read that straight off the table, and that's in terms of G, right? Or you could just read it off here. Okay, 2 seconds soil type D, it says 1.07 seconds. Sorry, 1.07 G. Okay, now so what have we got here? We've got this CHT for 2 seconds is 1.07 G, and you can convert it to, if you want to convert it to meters per second, okay, because that's what you're going to use when you use force equals MA later. The other thing, we found Z, or the hazard factor of 0.39. Now, we have ultimate limit state for 500 years and for 25 years. This is for the return period. Okay. Now, how are we going to find what we call the return period factors? For each return period, we have what is called a return period factor, and where that is in table. Here it is, table 3.5. Okay, so table 3.5 gives you the your value for RS or RU. Okay, so it's a little bit confusing because R is sometimes used for return period and is also used for return period factor. Okay, but I think you guys should be able to figure it out. Okay, so there's, I want you, okay, I've just put it up there. I want you guys to actually find it for return period of 500 years and 25 years. What is the return period factor from table 3.5? So you guys do that. Right, for the for 500 years, ultimate limit state, okay, 1 in 500, which is the annual probability of exceedance. Our factor is 1.0, okay, and for the serviceability limit state, 1 in 25 years, it's 0.25. Okay, so 1 in 0.25, just bear that in mind, and you can, okay, so we've got 1 in 0.25. We can now go ahead and find the acceleration CT for the ultimate limit state and RS for the serviceability limit state. Okay, so I want you guys to get the two accelerations. I want them both in terms of G and in terms of meters per second. Okay, so you guys do that now. Okay, guys, putting it all together, you've got the ultimate limit state for a period of 2 seconds equals 4.12 meters per second or 0.42 G. And for the serviceability limit state, C, for the same building of 2 seconds period, you got 1.07 G. That's 0.39, which is the same as here, but this time your return period factor is different. It's 0.25 to get 0.104 G, or 1.02 meters per second. So you guys all good on any questions about this? Okay. Now you guys have a go at this one. For a structure of fundamental period T equals 1.2 seconds, founded on soil type D in Christchurch for the maximum credible earthquake. Okay, this is way more than our design earthquake. We typically use this for when we're determining deflections. Okay, you got a return period of 2,500 years. Okay, find the response acceleration. Okay, so pretty much the same as what we did previously. Okay, so you guys give this a go. Okay, for this one here, you've been given the fundamental period, the soil type D, okay, and you've been given a return period. So we haven't given you the importance factor, or we've just straight away given you the return period of 2,500 years, right? So in terms of the importance level and the etc., we bypass that and just give you the what the return period is straight off. Now, what is our CHT? Well, let's have a look at our chart here again. 1.2 seconds. Let's have a look. So this is our spectral shape factor, the general, okay, it's a general one, and 1.2 seconds. Well, let's read it off here then, off the chart. And it's T1.2, and the soil type is D. So it's somewhere up here, and I estimate about 1.7 G. Okay, 1.7 G, say. And okay, so we've got 1.7 G. Now, what's the hazard factor? We need to know the Z factor, the location. Okay, so let's do that. Location factor. Christchurch. Is 0.3. Okay, so I looked up, I found 0.3 for Christchurch. And now the return, if you go to that table, okay, for the table 3.5, don't know why my screen's gone all blue, but that's all good. For 2,500 years, we've got a return period factor of 1.8. Okay, so we've got all our, we just got our three values that we need to multiply by now. So from that, we get CT equals 1.7 G times 0.3 times 1.8, 0.92 G, or 9 meters per second per second. Any questions there? Okay, good. Okay, now let's put together some of what we've previously done together with a New Zealand specific case, right? So determine the response accelerations for the structure below and also the associated base shears, and we'll talk about that soon. The column is a solid rectangular section, 150 by 150, with E equals 200 GPa. Assume the column itself has no mass. Okay, so the first one I want you to do is return period. Consider the case of return period of 500 years, location in Napier, soil type E, the mass M equals 2,000 kgs and height equals 3.5 meters. Now, it should be apparent that the first thing you need to need to calculate is what? You need the period of the structure, right? Because with the period of that structure, then you can measure off the, you can go to your tables and obtain the site hazard spectrum value. Okay, you can obtain the CHT, but you need T first. So I want you guys to work out T to start off with. Okay, so we'll give you some time to do that. Okay, let's have a look at, we've got I equals this, K equals this, and T equals 0.366 seconds. Okay, so if you go to your table then, and you look up, you got period, you look up what CHT is. Okay, sorry, it's the wrong chart. Open. Sorry, just give me a second, I'll get the code. Okay, so you've got CH, okay, 0.366 seconds for soil type E. Okay, so use this table for design. Okay, so okay, well, it's obviously within this range here, so it's just simply 3G. Now for Napier, okay, you can use this table to look it up by alphabetical order if you want. So 51. So Napier is 0.38, or you can get it off and you can see it's slightly less than Hastings, right? Hastings was 0.39, where Napier is 0.38, according to these contour lines. And for 500 years, the return period factor, okay, we're given the return period. So for 500 years, return period factor is 1.0. Okay, so given that, what is your acceleration? Okay, so you guys work that out. What is your acceleration in G, CT? This is your acceleration. I want it in G, and I want it in meters per second per second. Okay, so your acceleration is 1.14 G, or 11.2 meters per second. Now this base shear, how does that work? The base shear is simply, you imagine this, you got this mass here, right? It's got an acceleration, which we'll call SA, spectral acceleration, maximum acceleration of 11.2 meters per second. What's the force represented by this mass? Well, it's just force equals MA, which equals 22,400 newtons. So that's the force, that's the inertial force created by this mass here, goes through here. Obviously that transfers down to the base here, and you get a reaction called the base shear in the opposite direction, which is 22,400 newtons. And this is equivalent to a cantilever. Imagine a cantilever, you got a force down here of 22,400, you got a reaction going upwards at the base there. Sorry, at the left-hand support there. So is any questions on this? Okay, still another one. Okay, you got this, you've done that one. Okay. Let's look at the next problem for B. Okay.
Sorry,
Now,
there's actually no moment if it's like a cantilever, or
sorry?
there's no like sorry, there's no like moment on those kind of.
Yeah, there will be.
Oh, there would be. Okay, yeah.
But I'm just asking for the base shear for the moment. Yeah. Okay, for now. Yeah.
Oh, good. Sorry.
Yep. Okay, so there'll be obviously an overturning moment as well that you'd have to take account of. Yeah. So that's not a complete free body diagram, is it? It's just looking at it's just demonstrating the forces, not the moment. But yeah, that's a good question though. For completeness, I should put the moment there as well for the free body diagram. Okay. Yep. I might actually do that. I'll fix the PowerPoint up to include the moment, but the questions is for the moment. For now, is just to look at the base shear. Okay, so let's have a look at another problem. It might pay if you to write the you remember this is 0.366 seconds. Okay, save you having to work this out again. Okay. Oh, actually, you do have to work this out again, which is good practice. Okay, so let's start this question afresh. Do this problem now. Okay. Hey guys, for this problem, I get a period of 1.463 seconds. Everyone else similar? And from that, let's look up our forget what it's called exactly, the spectral shape factor. Okay, so we got a spectral shape factor for what is 1.463 seconds for soil type C. And I get about 0.85. Okay, so CH is 0.85. Now for Z, for the hazard factor, We're in Auckland, so Auckland seems about 0.13. You can look at the table here. Auckland is 0.13 for Z, and for 2,500 years, it's the return period factor is 1.8. Okay, so we can from these figures here, we can get the overall acceleration, which is 0.2 g. I mean, this is not the overall, the maximum acceleration, the maximum response, or we sometimes call it the spectral acceleration, which automatically means maximum, okay, under this earthquake. And what is our base shear? Well, it's simply mass times acceleration, which is 4,000 kgs times 0.2 times 9.2 g's times 9.81, which is 7848 newtons. Any questions here? Okay. Let's look at the consider multi-degree of freedom structures now. The structures we have considered so far consist simply of a single mass and vibration, which is the single degree of freedom structure, as we discussed before the break. What about multi-story structures? That is multi-degree of freedom structures. MDOF structures have many modes of vibration. Okay, so this is two stories and above. However, typically it is the first or fundamental mode of vibration that has the greatest influence in governing the response of a structure. Okay, so even though we've got higher modes, often we can rely on just that first mode, because that's the one that governs that's the one that has the most influence in governing the response of the structure. The first mode of vibration is found using a method called the Rayleigh method. The Rayleigh method is described in the code. Okay, so it's here, and we're not gonna use this, and you guys aren't going to be assessed on this. It's more for your interest. For this course, you are not required to use a Rayleigh method. The period T will instead be given to you. This is for a multi-degree of freedom structure. Based on T, you find the overall base shear on the structure in the same way as that of an SDOF structure. Once you have found the overall base shear, this total force is distributed up the structure to each floor level. This method, called the equivalent static method, is described in 6.2 of NZS 1170.5, which this is the code that you've been working with. Okay, so your overall V is given by the acceleration times the seismic weight, okay, the base shear. So it's acceleration times just, yeah, the weight. You don't have to CD, if this is G, right? If this is in G and you put it in weight, that automatically comes out as V. Or the other way is you can convert, if this is converted to meters per second, then the seismic weight would be M times G. Okay, so there's different ways to skin the cat. Where a structure has a ratcheting index, don't worry about that, in excess of 1.15, this base strength, and don't worry about that one. But this is the way you distribute your forces up the structure. It's based on, you've got your total Wi times Hi. This is a single figure that you get for the entire structure. And then the amount of force you get at each level is Wi over times Hi divided by the overall Wi Hi. That gives you the ratio times the base shear times 0.92. Okay. But when you get to the top floor, you add the final 8% of the base shear to the force. Okay, and this takes into account what we call higher mode effects. Okay, so we don't have to worry about it too much. It's just a rule we need to know. For the top floor, it takes 8% of V plus this ratio here. So if you guys can just write this down, and we'll go for an example. Okay, so just write down this equation. So it's including this as well. Okay, and then so we'd have to keep on referring back to the slide. So you guys can do that first. Okay, so let's look at this. Sorry. We'll go, we'll look at more detail on this equivalent static method. The multi-story compared with a single story structure. So this is a single story one, and this is the multi-story one. But nevertheless, the first mode of vibration, which the building simply swings back and forth, will still be will still have the largest effect. Okay, so while the structure of 3 modes of vibration, the first mode of vibration is the one that is most influential. Okay. However, unlike the case for a single story building, we need to use a different method to calculate the period T of this fundamental mode of vibration, which I've talked about before. And a concentrated mass within H3/2 above and H3/2 above and H2/2 below this floor level. Okay, so this just tells you this how do the masses distribute for a multi-story structure. M1 takes into account this one halfway of H1 and halfway of H2. M2 takes halfway, concentrates all the mass between this level here, halfway along H2 and halfway along H3. And M3 takes all of the roof and halfway down H3. That's just telling you how the masses are kind of distributed. Okay, so here we've got a problem. The period of the structure founded on soil type C is 0.5 seconds, located in Nelson. Find the ultimate limit state acceleration return period of 500 years, the base shear, and the force at each level. So already we've given you the total masses at each floor. So imagine this mass here, right? 15291. It takes the mass halfway from here, halfway here to halfway here, and likewise for the other masses. And this one here considers a roof mass plus halfway down the top story. Now, how do you get the total? How do you get the? What do you start off with to get the total base shear? Well, you get the total base shear by first finding the response acceleration, which you've already done. You've got return period of 500 years, period of the structure is 0.5 seconds. You've got the location, so you should be able to find, to start off with, the response acceleration based on the first mode of vibration. So find the response acceleration, okay? And then what do you do for base shear? You add up all the masses and multiply it by the response acceleration. So do that part first. That first part should be easy to do. Okay, so because you're given the period, you're given the location, you're given the return period. So I want you guys to find the response acceleration. I want you to find the base shear, just use the total mass, and then we're going to talk about the force at each level. Is that okay?
Yeah, that's good.
Okay, good. Hey guys, you've got the situation here. Okay, we've got CD CHT times Z times R. Okay, so we consider soil type C. Okay, period of building is 0.5 seconds, and we get around 2G. Our site hazard factor is Nelson. Okay, so it's 0.275, and 500-year earthquake is 1. So that gives us CDT equals 2 times 0.27 times 1.55 G, or 5.4 meters per second per second. Okay. To calculate the base shear, it's just mass times area. So we get the total mass of the building times CDT, and that's your total mass times acceleration is this. Notice in the they go like this. They go the weight, seismic weight times CDT. That means when they go seismic weight times CDT, they've assumed that you haven't converted to meters per second yet. They assume that you're still with 0.55 G. So if you leave it at 0.55 G, well, then you multiply it by the seismic weight, okay, to get exactly the same answer. So I've already changed the CDT to meters per second, so I don't have to use the seismic weight. I just use the seismic mass. You'll get 371,569 newtons.
Yeah.
Okay, cool. Now, the next thing to do is this. Just go back to this equation. Okay. I want you guys to get, okay, so that's your overall base shear. I want you to work out what your WIHI is for each level. Okay, the size, in fact, you can just use mass times height for each level. Don't have to worry about W, just mass times height for each level. Okay, so this to start you off, let's go back here. You've got this, okay, figure here, everything's 4 meters story heights, right? So you only have to do it twice, right? So I want the mass times the height. Oh no, you actually do it for each time. Mass times the height for floor 1, 2, 3, and 4, and 5. Okay, so I'll just rewrite that for you. Okay, so right, you can just use MI. It doesn't have to be WI. MI times HI, where I is the floor level or roof level. I'll just say for where I is the level number. Okay, so I want you to do MI. So the first one would be what? The mass would be, the first one would be 1 for level 1, would be 15291 kgs times 4 meters, right? For level 2, 15291 kgs times 8 meters, etc. You can do it on, in fact, you can, okay, so I want until you get until for level 3. You can obviously do it a quick way, but I just do it so that you guys can times 12 meters for level 4. You've got same thing. $16 meters, and then for the final one, for the roof, you've got 7645 kgs times 20 meters. Is that correct, guys? Okay, it's M1 times H1. Okay, now you can, this one here, you can do it very quickly. You just add up the add up this multiplied by that plus that. So I want the total. So what I'm wanting here is this thing here. Okay, so if you look at this, I want this value here. Okay, this is summation sign. It means the sum of WIHI plus the sum of W1H1 plus W2H2. Okay, so summation sign that you would have done for mathematics, but this value can just be provided by this. Okay, so you guys do that. It'll take you about a minute, okay, to add all that up, because you can just do that by 16 plus 12 plus 8 plus 4 times that, then add that. So quickly don't worry, quickly calculate that, the overall. Okay, so I work out the sum of MIHI is this here. Okay, that's that value there. I know in the code it goes WIHI, but we can just use MIHI because it won't, because this is just a ratio, right? So all the G's divide out anyway. Okay, it's just a ratio. Now this gives you a ratio of how much of, you've got your total V, right? Which is all good. You've got this total V of 371,569. What is the proportion of V at each level? Well, at each level, it's whatever this individual value is, okay, individual value divided by the total. Okay, so it's WI over HI. So I want you guys to give me the ratio, okay? How much of the force, how much of V goes into each level? Okay, so proportion of V. Okay, so you should be able to work out that and then divide it by that and then divide it by 0.92. I mean, sorry, multiply 0.92 for every level. Do that for every level first. Okay, so this part of the thing, mi times hi times 0.92 times this. Okay, it's based on this equation here. Okay, the only difference is we're using mi rather than the mass rather than the weight. Okay, so it's the same idea. So you get the mass times the height divided by the total, the sum of the totals, and multiply it by 0.92 to get the proportion of total base shear. Do that for the roof as well, and then we'll talk about the roof. So get those proportions now. You guys can do that. It's good to just plug it in your calculator to do it once, and then later on you can use spreadsheets or whatever. Okay, guys, so you can see how I've calculated the first 4 levels. I made a mistake there because this is a smaller mass, so I'll just correct that. Okay, so this is 0.2 here. And this is 0.28. Okay, so that should come to around, well, should come to, I've got 1.0 and I've just got a little bit more, but let's just say 1.0. Okay, so these here, what are these? This is we're calculating here our proportion of total base shear. Okay, total. Okay, so at each level, this is how much base shear of the total base shear each level will take. Okay. Now we calculated for our total base shear. Okay, if you remember 371569. So all you have to do is multiply each of these by 371,569, okay, newtons to give you the force at each level. Okay, so that's all you have to do now. So I know it's a bit tedious, but it's good to do it once so that you get the hang of how to do it. Okay, so okay, well, it doesn't mathematically make sense, does it? So I'll just make it. Okay, so just give the answer there. I know it doesn't mathematically make sense because you've got this equal to that times that, which doesn't, this equals to that part, right? So I'm going to copy it again so that I'll just go along a bit. I'll just recopy it. So you got this value here, these values here. That you can calculate like this. Okay, so you guys just go do those answers now, right? Okay, so you got them at each level now. So you can just go for level 1, 2, 3, 4, just get the numerical values out. And I'll take it out from here because it doesn't mathematically make sense. Okay, so we can move that back up there. Okay, so you're going to get the base shear now. Okay, so just calculate that once to get your to get your forces at each level. Guys, these are the numbers I got, and that's pretty close to our total, isn't it? So our total was 371 or something. So there's some rounding error there, but it's within about 1 or 2%. Okay, so is that what you guys got? Something similar to this?
Yep, yeah, quite similar.
Okay,
Yeah.
good. Okay, so I'll just show you. Okay, so that's what we've done here. Now I've made a mistake in this one, so I'm going to have to correct it. It means it's a bit different from what we've got. Well, it's quite close anyway, but I don't know why I put 30 meters here instead of 20 meters. Okay, but the principle is pretty much the same. So I'll fix up this final result. Yeah, so there's one more there that you guys can do for practice. I think I've finished giving you the answers. Yep, so I'll fix up this PowerPoint, but that's pretty much it. It's pretty reasonably straightforward. It just centers around distributing the forces based on a ratio of the mass or the weight times the height. Okay, and yeah, so that's all you really need to know for seismic loading. Is there any questions before we call it an evening? Is all good? Okay, so I'll see you guys next week then.
Thank you. See you next week.
Thank you.
Okay, see you guys.